Well, it's a great pleasure to be able to talk about someone else's breakthrough, which is mostly what I'll be doing. So the sphere packing problem in d dimensions is a problem of how many points you can fit into space such that no two are less than distance 1 apart. Okay, so you can ask, what's the biggest portion of space that's filled by non-overlapping equal-sized spheres? Let me just put it this way. Okay, and of course the problem is scale invariant, so I'll change the scale at will for convenience at various times. And so the seminar title is Geometric Structures in 3-Manifolds. So I'll start with R with 3 dimensions, just so I have a 3-manifold in there. Okay. So, so the problem for 3 dimensions was posed originally by Kepler in 1611, and it was solved by Tom Hales in a series of 2 papers. Well, 2 works. One is a computer check of the first. In 2 dimensions, it's actually already pretty subtle.
I think the analyst decided in 1998 it was okay.
Okay.
It was okay unless you wanted to have a stamp of approval.
Okay. I certainly didn't want to wade into this. Tom, if you're watching, I accept both. Anyway, so in 2 dimensions, even there, it's relatively subtle. So there's a paper of 2A in, I think, 1892. There's work of Fayez Toth in 1940, which I think is considered to be the first rigorous proof. And the answers are, I'm not going to describe the actual configurations here, but they're, of course, well known for 1 and 2. One thing that's interesting here, by the way, there's one unique answer, which is the honeycomb sort of hexagonal packing. There's multiple ways to achieve the optimal density in 3 dimensions. And then d equals 1 is trivial. And now, in the last few weeks, there's been 2 new entries on this table. Okay, so the first entry by Maryna Viazovska. Okay, and this is so that's pretty recent. And then exactly 1 week later, I mean, I'm going by the archive posting dates here. So 5 of us did it in 24 dimensions. Okay, I don't have any. You notice the sequence has stopped at this point. There's something very special about 8 and 24. We can't expect every week to keep proceeding like this. What I really want to talk about today is the story of how it's possible to get this in 8 and 24, and of course leapfrog all these other dimensions that we still have really no idea how to do. In fact, we don't even know what the densest candidates are in many of these dimensions. Okay. So let me just state this a little more precisely as a theorem, because it's a little bit stronger. There's uniqueness. So Viazovska has the exact same statement for 8 dimensions, more or less. I mean, just you change the numbers. The same qualitative statement. So, so this is the theorem for 24. Okay, so I'm saying a lattice is the densest packing. That simply means you put spheres at every lattice vector and make them as big as possible until they touch. Okay, so this means it was already known by Cohn and Kumar a little more than a decade ago that among lattices, this is the best packing, which is itself remarkable because we know that up to dimension 8, but not from 9 to 23. Then you can ask about uniqueness. So one has to state uniqueness carefully. If you take the best packing and remove one sphere, well, density is measured asymptotically. So that has the same density. And you can do this in obviously many ways. You can start removing things. So the fair thing to ask is about a periodic packing. So periodic packing means that you take a big box and you translate it by some other lattice. So a periodic packing has balls centered at a finite union of translates of some lattice. And among periodic packings, the uniqueness part I'll state right now is that the Leech lattice is strictly the densest packing. So this is a statement which is just false in 3 dimensions. It's now true in 2, 8, and 24 dimensions, of course, also in 1 dimension. Okay. So I want to mention that just yes, in 8 it's the E8 lattice, and now's a good time to put some information about the lattices up. This is all that sort of maybe a human can be expected to walk around memorizing about the E8 lattice and Leech lattice, but except for, of course, Conway. So the proof doesn't use very much about the E8 lattice or the Leech lattice. Okay. Okay, so these are unimodular lattices. That means they have covolume 1. And the key point is the vector lengths. So the vector lengths for the E8 lattice are square roots of even integers, positive even integers. The Leech lattice has the same vector lengths without this one. So the shortest non-zero vector in the Leech lattice has length 2, which means you can put a ball of radius 1 at every lattice vector. That's quite a bit stronger than here. Okay, so actually, if you want to prove a sphere packing is optimal, notice if you want to show that you can't beat a certain density, you don't have to consider every possible packing, although the proofs in 2 and 3 dimensions more or less do. There's a reduction to periodic packings. And it suffices to consider only periodic packings to prove a sphere packing bound. The reason is, let's say you had some crazy packing that wasn't periodic, but beat whatever bound you're trying to get, like the Leech lattice is bound. Well, that means at some point very far out, it will have beaten it. If you take a big box that far out and repeat it, then that will be a periodic packing with density less than what they're supposed to beat. Okay, so now one thing that
Can you say that again?
okay, so let's say I have some funny configuration of spheres that somehow beats the record in the plane. Well, if I take some very large box, within that box I'll have strictly better density than the record I'm trying to beat. And then I could just repeat.
No, by definition.
Just by the definition of density is you take a limit as the size of the box gets bigger and bigger.
That doesn't work in dimension 2 and 3.
So this reduction works in any dimension, yeah. Yeah, so it's more or less just a definition. Okay, well, one thing I want to point out is that it's nice that all these names can be claimed as number theorists, or at least their advisors are number theorists. Right, to a bit of precision. Again, I don't know who's watching this. But I mean, that's a striking factor. And in fact, the argument here I would say is to prove this theorem, and Viazovska did in 8 dimensions, which is following essentially the same argument. We're following Viazovska's argument very closely, is a proof in analytic number theory. So certainly it's fair to say it uses ideas from analytic number theory. What? What? I don't criticize anyone's advisor, especially in their presence. Okay. Okay. Okay, so I'd like to center the talk mainly about these ideas because they're very striking. When the ideas themselves are unexpected and they reduce a problem, ultimately it has to do with geometry into something, and then to functions in one variable, and then to modular forms. Okay, so there's an idea going back to Siegel, and then followed up with an important sharpening due to Cohn-Elkies, to use the Poisson summation formula. So let me write out the formula in the way that's useful here. So here lambda will be a lattice in RD. And this is the co-volume. Or if you take the basis vectors and write out a matrix with them, it's the absolute value of the determinant. And this set of lambda goes over the dual lattice. So that's a set of vectors whose inner product with the original lattice vectors are always integral. And f hat is the Fourier transform. So I mean, as a statement, you can start relaxing conditions about what f is. I'm going to think of f as a Schwartz function. And I'll normalize the Fourier transform this way. Oops. OK, so probably all of you have seen this formula in one dimension when it's a sum over the integers. If you iterate that d times, you get the formula when you sum over the zd lattice, which is its own dual, and whose covolume is 1. And then if you replace f of x by f of ax for matrix x, then this pops out by transformation law. So it's really not any more complicated than the traditional Poisson summation formula. It just has more features in it. Okay, so I can figure this out. Start this one. Okay, so let's make a hypothesis for a moment. Let's suppose that the Schwartz function f is negative outside a ball. We'll also assume that the Fourier transform is non-negative. Okay. So Siegel studied conditions like this with functions of compact support. And Cohn-Elkies made the important allowance that you let the function be negative. Otherwise, Siegel's story doesn't get very far because you can optimize everything and it doesn't gain very much. But it's key to allow the function to be negative. And now let's just drop terms in Poisson summation. Now this is a positivity argument in analytic number theory. And the key to such an argument in analytic number theory is not to drop too much and not to drop things that cost you too much. We're going to drop basically everything. And that's usually a bad sign in terms of being sharp. In fact, almost basically only one example where that works to be sharp. Okay. So if we drop terms, well, let's also assume that lambda has no non-zero vector. Of length less than r1. So r1 is going to be the shortest vector. r1 is square root of 2, say, for the 8 lattice, or 2 for the Leech lattice. These are self-dual, yes. So I'm going to drop everything on the right-hand side except for the point 0. I can do that. The function's positive. On the left, well, under this assumption that there aren't short vectors, I can also drop all the non-zero vectors. So I get the following inequality. I get that f of 0 is at least f hat of 0 over the covolume. Or in other words, the covolume is bounded below. So this is a relation in which I've set the length of the first vector more or less to be r1, and I learned that the volume has to be big. This is giving an upper bound on the density of a sphere packing that comes from a lattice. Okay, so this is for lattice packings, and the theorems for lattice packings were, of course, known. But for a regular packing, you can still apply this idea, just if you take a bit of a different form of Poisson summation. It's very similar to, I guess, for number theorists, it's similar to the adelic Poisson summation that's in Tate's thesis, where you have an action of a finite group. Here, there may not be a group. So for periodic packings, so let's assume that periodic packing is a union of translates of some lattice plus vectors Vj. We apply it to this form of Poisson summation. And this is something you can derive from the previous form of Poisson summation just by shifting the function and computing how the Fourier transform changes under a shift. Namely, it multiplies by a phase. So now there's a square on the right-hand side. So now in this formula, the right-hand side retains the positivity features from before. And if there are no centers of the balls, distance, obviously I mean distinct centers, less than R1 apart, can again drop terms. So the only way this would be where the function is positive is if this is bounded by R1. And this assumption rules out that possibility, because lambda plus Vj is a center and Vk is also a center. We again drop terms. Now, the only thing that comes up here is when lambda is 0 and j is equal to k. So we get n times f0 is at least n squared on this side, because the term when lambda is 0 has n squared here for that sum. F hat is 0 over lambda. And now this is giving qualitatively the same bound, if you follow it through. So this is a key point. This is what allows number theory to enter into a question that involves any possible configuration. So there's first the truncation to a large ball, and then repeating the ball using this variant of Poisson summation. OK, so it's rather unlikely such an estimate is sharp. But it's not surprising you might improve previous estimates, say in some general dimension using such an argument. Cohn-Elkies embarked on a project to do that. This was a big part of Henry Cohn's PhD thesis, which was, I guess he got his PhD in 2000. They improved bounds on densities in all dimensions up to 36, except, of course, the dimensions was known. Maybe it's starting with 9, actually. But anyway, they improved, starting with 8. They improved a number of density bounds. But the most striking thing to me was that they found by numerical optimization, they get incredibly sharp bounds, incredibly good bounds, not quite sharp.
You should point out this was in your program.
Yes. Well, you just did. But, in certain dimensions. So you could run this for dimensions where Sir packing is completely understood, like dimensions 1 or 2. And in these dimensions here, the bounds were, well, the longer you run the computer, the more the bounds converge. There seems to be no limit to this linear programming mechanism, which is, of course, an optimization to at least approach the right values. And in fact, before a few weeks ago, already the variances technique, which I'll mention later, that Henry Cohn and I did, had bounds for 8 and 24 that were within about 10 to the minus 70 of each other. So the bounds were converging, but there was not a theoretical proof of it. OK, so then you can ask the question, is that could this method actually be sharp? So the method is construct a good function with these positivity properties of it in its Fourier transform. Could it actually?
There's no lattice left because you explained it. But
Yeah.
the linear program is just on F and F.
Yeah, and right now it's in RD, but in a moment I'll explain this reduction to just the real line.
How do you know the index n?
Well, you don't know the index
You
n.
build that into the linear program?
No, because it's all you need is the positivity. So the
But in the bound,
so the bound that so I'll basically
you get downstairs,
there's an n. Okay, so what really you get here is you get the volume covolume of the lattice divided by n is what comes after you cancel the n's. But that's sort of an invariant because if you decide to take a bigger box, you'll have increased the size of the lattice just as much as you increase n. They compensate. Okay, I should write here. So this gives a sphere packing upper bound. So I just want to embark on a little discussion of what we would need for this to actually give the correct answer. And the main thing it needs is to not disprove anything else we know. Namely, you can't put a function in which will violate what we already know about the E8 lattice and the Leech lattice being, in fact, they provably were known already to be the best possible lattices. So it can't, if you apply it to Poisson summation over the E8 lattice or the Leech lattice, you can't lose any information. So applying to E8 and R24, or the Leech lattice. Sorry, yeah, R8. That was bad. So that means that, well, all these terms that we threw out in dropping positivity here have to vanish, which is actually all the terms except for at the origin. So f and f hat must vanish.
I have a question. Why did you drop 2 in this one?
Why did I drop 2?
Yeah. I mean, so far the bounds you're saying the linear program bounds also worked at 2.
Yeah. So the answer is I don't know how to get this to work for 2. It'd be, I mean, I'd like to see it done, but I don't know how to do it.
So this method is not achieved.
That's right. In fact, the proofs that in the end, I think the proof of sphere packing in dimension 8 and 24 could be said to be simpler than it is in dimension 2. Okay, so f and f hat have to vanish on all non-zero vectors in the E8 or Leech lattice. But of course, there isn't the E8 lattice. It's a lattice up to isometry, which means you could rotate the lattice. So here I normalize them to be self-dual, so I can't stretch them, but I can certainly rotate them, okay? Or rotations. And this is an argument that Cohn-Elkies give. So that means that f and f hat vanish on the concentric spheres where all the non-zero vectors live. And they also satisfy positivity conditions, which are given only in terms of the norm. So at this point, I can radially symmetrize f. If I do that, I radially symmetrize f hat at the same time. So if we radially symmetrize, so then we will identify f and f hat as functions on the real line, say, or from 0 to infinity. they vanish at the root lengths. Okay, so now we've not only gotten the lattices out of the picture, we've gotten the dimension out of the picture. It's just now a problem of one variable. Wow. So I like to draw a picture of what these will look like. And now I can actually draw a picture because it's in one variable. So we're trying to construct f and f hat, which now, again, f hat is not the one-dimensional Fourier transform. It's the radial Fourier transform. But you can write down a kernel with Bessel functions in one variable. That's not a big deal. Okay, so we still need appropriate sign changes. So I'll draw a picture of what we need. Okay, so here's f. Okay, so f will start off being positive. Well, we want, in the end, to prove the right bounds. They follow from three conditions. So one is that f hat of 0 is equal to f of 0. So then this ratio is 1. And I mean, say for the Leech lattice, it's unimodular. So that's the right bound to show. And then the second one is the Fourier transform being positive. And the third one is now I'm thinking it's one variable, this being negative, or at least non-positive for r at least r1, which is the first non-zero lattice vector. That's either square root of 2 or 2. So and we can normalize these to be 1. It's just you can multiply by a constant. So we'll start off at 1, say, and then it will cross at r1. And now it's got to vanish at r2, the next non-zero vector length. But it can't vanish to order 1, because if it vanished to order 1, it would shoot up across the real axis and be positive again. So it has to vanish to order 2 or maybe 4. The simplest thing to guess is it would vanish to order 2, and so forth. It can never go up again. So it has to have double zeros. I mean, it could be quartic zeros, but I'll write double zeros here. It should really be a first order 0, and then second order vanishing. At these points. And f hat is easier to draw. F hat starts off at 1 also, but when it gets to r1, it has to go back up again. So it should have second order vanishing. Yeah, I mean, you can relax the yeah. Yeah, so the functions in the end are Schwartz functions, but in Cohn-Elkies paper, they allow something more general. I think it just basically has to decay fast enough to make things converge. Yeah. So one thing that's convenient to do is to diagonalize under the Fourier transform. So let's let f plus and f minus be defined simply by averaging the functions and dividing by 2. Okay, so f plus is an even function under the Fourier transform, under the radial Fourier transform, and f minus is an odd function. And now the graphs, since this will be important, let me draw the graphs again. So now f minus has to vanish at the origin, but by smoothness, it can't just vanish to order 1. It's a smooth function when it's radially symmetrized. Otherwise, it would have a conic singularity there. So it has to vanish to order 2. And then it goes down and becomes negative. So okay, so this is again at R1. And this is at R1. I guess these aren't at the same scale. So now it's just a question of getting the right zeros at the right places to the right orders, but also to have no other zeros. Because if there was another 0 here, then these things would not be crossing the real line, but from the top, and that would be bad. Okay. one thing I didn't write on the board, but in the Cohn-Elkies scheme, the uniqueness statements follow from not having any additional zeros as well. Because if there was something there, if there was another packing that met that density, the function would have to vanish at the root lengths. And they show just the polarization argument that you must have a lattice from that. And that's what the lattice is. Okay, so let me write down these conditions here. So, and I'm going to write on the board a bit more in a second over there. So f plus and minus vanish to first order at R1. And again, when I write this here, I'm really mean on the real line because I've tacitly identified a radially symmetrized function with its value on any ray. And then the derivatives, it's not clear from the picture, but the derivatives have to match because we want when we subtract them to get f hat, we want it to vanish to order 2. So the derivatives have to cancel each other. We'll normalize f plus of 0 to be 1. And then f minus of 0 and its derivative will vanish. And then f plus and minus, f plus minus both vanish to order 2 at every other lattice length. Okay, so we're pinning down some conditions at the origin and at the first lattice length, and then every other lattice length, it's just second order vanishing. Okay. So we're going to write something down about these functions in a moment. Let's come back to here. Okay, so Cohn-Elkies studied, they were studying the linear program, and in the course of doing so, came to the conclusion that there should be some function with these properties, and they had some information on it. What they did is they didn't force these conditions about the root lengths at all. They put them at different places, and then they moved them along to see where they would get better packing. So they moved each 0, and they optimized it, and when the program stopped, they had very good bounds. And that was used by Cohn and Kumar, for example, and extended by them to prove the Leech lattice is the best lattice packing in 24 dimensions. I want to mention a project Henry Cohn and I then began at that time. And the idea is we wanted to study, once we became convinced from that there must be some function that solves it exactly, which is clear from their numerics. They got many digits of the upper and lower bounds to agree very quickly. We were fascinated by the function. We wanted to just get our hands on some of the properties. So I guess this is maybe a fair way to put it, is that we gave a construction, but I'll put the construction in quotes, of f plus and f minus, and of course, thereby f and f hat. Okay, so using determinants of orthogonal polynomials, well, they're Laguerre polynomials. Yeah. So this is a way to control the Fourier transform properties and to get them to vanish at certain places. But we again didn't, so it's a deterministic sequence. Every term of the sequence is non-zero. We can't prove anything about the convergence. We can't prove they converge to a limit, much less if they did converge to a limit, we wouldn't be able to prove the sign change properties. So so this is certainly a failed attempt, but there are some things that we can get from the failed attempt. So one of them is that we can, at least by looking at these functions, say with very high degree polynomials, we get better and better bounds for sphere packing. So we improve the upper bounds. I mentioned this before, but I'll write it down. Well, I'll be conservative and say 10 to the minus 60, but it was actually significantly higher than that for E8. It was something like 10 to the minus 80. But anyway, at this point, this is more than the number of atoms in the Earth. So if the Earth was 8-dimensional space packed by the E8 lattice, you couldn't stick another one in at that. Okay. Okay. Now, we didn't actually rigorously check that there are no other zeros because there's no point to doing this to write out a complete rigorous proof. But certainly we got the functions where basically the difference is that these values are very close. They're converging to 1 in the limit, not quite 1. Okay. Okay. And then as part of that, well, there's high precision numerics. And I think this is perhaps the main feature. We can compute this function f and f hat at any point we wanted and find out things about it. We just couldn't prove that was what we were doing. But at least we get some information about this fascinating object. So as Peter likes to point out, there are very few extremal functions that come up in number theory, and this is one of them. And since we were not able to write it down, maybe we could at least learn something about it. And what we found, we identified some rationalities. In fact, every time we sat down and looked at it for a week, we would find another rationality. And that's probably why we didn't get this thing done, because we just kept finding more things and never deciding when to stop. But, OK, so this is the most striking thing. I'll put some more on the board in a second. But the rationalities clearly point, I'd say, to modular forms.
What do you mean rationality?
OK, I'm going to point down I'll write out examples in a second. Okay, but I mean, this didn't help us, at least not until we saw Maryna Viazovska's breakthrough. So let me give an example. This is a little unnatural looking, but it's got some nice numbers. So if we look for d equals 24, if we take the even eigenfunction as a function of x, we take this linear combination. I'll write other ones in a minute, but I just like this one. OK. So this number is an important number in number theory. It's the 12th Bernoulli number. It comes up in the study of Eisenstein series. It doesn't come up for any other reason than that. In fact, Wikipedia even has a quote that it's like a radioactive marker. If you see 691 coming up in a computation, you know there are Bernoulli numbers there. OK. So there's something arithmetic about this function. And this is coming from a a big decimal, and that number is identified from it. So let me put in my table here, which I've left ready for it. I have some more rationalities. These are the ones that are useful for. So I didn't write entry for R1. So here are the eigenfunctions for small x. So this is what it is for 8 dimensions. OK. This is what was identified numerically. So we were looking at orthogonal polynomials times a Gaussian with a pi in the exponent. And when I first ran this, I had some big decimal expression, and I found the inverse symbolic calculator website. I figured, why not? Maybe I'll figure out what the number is. And I put this ugly number up there, and it said your digits occur in somewhere in pi. And so I thought that's worthless, and I clicked the X button, but the lag from my hand, my head to my hand to my eyes was pretty big. And just as it was closing, after I told my hand to click the button, I noticed it said starting with the second digit. So I redid it, and I realized, oh yeah, I was supposed to subtract out that pi. So the number I had was 1.04159265, right? So it was really minus 2.1. Okay. And then, so the important point is it gives quadratic information. So here it's Okay, while I'm at it, let me just write out a few other pieces of information for the 24-dimensional one, since these were important for us in solving the 24-dimensional case. Okay, so again, this just comes from looking at it numerically and having some intuition why it might be rational, and taking its reciprocal and seeing it's an integer. So it took a little while to hunt some of these down. Some of these things vanish. Okay, so there's a few more there. Okay, so these were all found numerically with some hints as to why they might, like, if there's a square root of 2 in there, you obviously might want to have a hint as to why. The reason is if you actually dilate the lattice by a fixed factor and differentiating the dilation factor near 1, you can prove you can prove some relations of that type, not that different from this, and so it's not surprising. So there actually is some theory that went into that, but these are all at this point numerical observations.
So I thought F plus was only meant to have zeros at the number, root 4, root 6, root 8.
Yeah, so F plus, this is a derivative so it's F plus is non-vanishing at square root of 2. Oh,
No, it's non-vanishing.
yeah, F,
Leech lattice.
it's sort of Leech lattice. F minus does vanish there. Okay, anyway, so since I'm running a little short on time, just the other thing I want to say is you can deform, in this method with orthogonal polynomials, you can deform the dimension. So this is now a question of one variable where d is no longer necessarily constrained to be an integer. And when you deform, you get even more sets, more sequences of rational numbers. We were never able to piece them together, but now things make sense with Viazovska, and we certainly see 691 again. Now, what Maryna has done is spectacular, and one important feature in my mind is it explains why we had order 2 information about the function at every square root of even integer, even the ones that weren't lattice lengths. So let me give you my interpretation of what she did. She takes the function and divides it by sine squared, essentially, which is where to get most of the zeros out of the way, and then she writes that as a Laplace transform. So let me write out first for the odd eigenfunction. Okay, so she wrote this out. I'm giving you my interpretation of it. I believe the way she came across it was different. I'm more starting at the endpoint because it's like I recognized structurally with other things I know, but there's many ways to interpret it. So she's going to factor out, we want this to vanish to order 2 when r is the square root of an even integer. So it makes sense to try and put a sign there, but you're going to have some poles for, say, when r is 0 or square root of 2 or 4, depending on the case. And then she writes this as a Laplace transform. So I'm thinking here of this is the imaginary axis in the complex upper half plane. She's going to write it as a Laplace transform in Z. So this was only going to make sense for r large. Okay. So this there needs to be a radial Fourier transform. So it has some of the 0 conditions built in. And this type of integral is easy to continue analytically if you know this has say a power series expansion or Q expansion. So the key idea is that, at least let's assume 8 divides D, because those are the only 2 cases that matter. This is an eigenfunction of the radial Fourier transform with eigenvalue -1 if the following condition holds. So this is a modularity relation. So this means it's saying it inside SL2Z, where the diagonal entries are odd and the off-diagonal entries are even. So this looks like a modular form for a congruent subgroup. It's actually a free group. Gotta get some topology in here, right? It's a free group on two generators. Its weight will be negative. So this actually did emerge when Henry and I saw these numbers. We tried some construction related to something Wilfried Schmidt and I had looked at with where the discrete series sit inside principal series. This number is pinned down by that just as well. This is where there's a duality of representations. The even one is certainly not the case. It's much more complicated. But anyway, it's modular, but it may have poles at infinity, for those who know what that is. So it's holomorphic on the upper half plane, but as you take z up to the top of the upper half plane, it may blow up exponentially. It may have poles at cusps. But at least this structurally this is a key idea. She has one for the even eigenfunction, which is more complicated and really very key to her breakthrough. Okay, so we certainly, Henry and I think it's fair to say, certainly had no idea how to construct eigenfunctions from the modularity, despite the hints of it. The things I tried were too simple. The idea of factoring out the sine squared in particular is very important. Okay. Okay, so we have a different integral here, or the even one. Okay, so again, this will converge for R large, and there's some relatively straightforward meromorphic continuation. But the key thing here is what property do you need on this function phi?
Psi is,
I'm going to write down what it is in a second. So yeah.
modular and the transformation property. It's got a certain behavior at infinity, otherwise holomorphic.
Yes. Yeah. So that's a Q expansion, for example. Okay. So okay. So phi is.
You're complexifying the variable R.
That's right. No, not really. We're complexifying z. We're really complexifying z. I mean, it's not.
For psi.
Yeah. Okay, so there's a notion of quasi-modular form, and here's the weight. And this is now for SL2Z. So rather than define for you what a quasi-modular form is, and first I'm just going to write an exact expression, but it has the following form. It's basically a polynomial in the Eisenstein series E2. So I'll put these up on the board in a second. E2 is not a modular form because its transformation law is slightly different. Okay, but so she identified in a very key way that this structural property gives even eigenfunctions. Okay, so this is now modular, again with poles at infinity perhaps. And here are the weights. So it's 4 minus d over 2, and phi 1 has weight 2 minus d over 2, and this last one is weight minus d over 2. Okay. So I'll write down the definitions. But from this and meromorphic continuation, you can start to see all these properties emerge. In particular, it explains why all these things we had stopped at quadratic terms, because there's a sine pi square. Oh, should be a square. Okay. Okay, so I have to put the definitions up.
The method is to write down phi and then define f plus f.
Yes. Yes. I mean, well, so more generally, I mean, she has. Yeah, I mean, she has a method of constructing eigenfunctions from modular forms. I'm going to write that right now. Okay. Okay. So how this board will be about the even eigenfunction, and so I'm switching the order here. Okay. So ek. So I'm going to have k equal 2, 4, and 6 here. This is the Eisenstein series defined by Eisenstein. as opposed to what I talked about last time I was here, which is something on the group E8, which is not the lattice E8. Yeah. So we sum over divisors, and then there's an, I'm sorry, this is probably not legible, so I'll write it here. So this gives a Q expansion, and this is one of the first examples in the study of modular forms. Okay, so E2 is not a modular form. It has a transformation law that's something like E2 of -1 over Z, which should be something like, I'm gonna get this all wrong, but it should be something like this, but it's that minus 6iz over pi, I think. So it's a bit off, and that's why this is called quasi-modular. But that's crucial for this property you need here. Okay, and then there's Ramanujan's delta form, which is a cusp form of weight 12. So the first cusp form. It's probably better for these formulas to not divide. For E8 and for the Leech lattice. So this is a reinterpretation, just a rewriting of what she has in her paper on the 8 lattice. It's the square of E2, E4 minus E6 divided by Ramanujan's delta. In particular, you have positivity immediately from this formula. Okay, and then in the Leech lattice case, 25 E4 to the 4. I don't know if you really want to see it, but this is about halfway through the formula. Okay. That's what it is here. So how is this identified? Well, we have these lemmas here that tell you what space to look in. Then you have to find it. But then we have all this information here, and that's easy. It's easy to pin it down with that. In fact, I don't think you even need all this to pin it down, but at least that's how it was done. Okay, now the odd eigenfunctions, I'm going to write things again differently than she has, just to make the positivity more apparent and to explain how it was computed. I want to write down some of the classical theta functions Jacobi studied. This? Minus?
E6 squared times E4.
I wrote E9, yeah.
E4?
It should be E4, yeah. My font was too small here. Okay. If you had written, my death warrant, I would have written that on the board instead. So for the odd eigenfunction, so let me write down some of Jacobi's theta functions. So again, these are the earliest modular forms, really, Jacobi's and Eisenstein's. So 0, 1 is the same as 0, 0, except the coefficients alternate sign. I realized every time I write here, probably you can't see any of it. I should put the whole talk here. You'd probably be happier. Right? And then this theta 10, or theta 1, 0, I guess. This is a little funnier. There's a shift of a half. So these are all modular forms for gamma 2. And they sort of each isolate different cusps. All the sums over the integers here. And then the formulas now are very similar. So in the case of E8, I like to write her function like this. So again, they're all being divided by delta. Delta is a non-vanishing cusp form. It has a famous infinite product. It's the eta function to the 24th. So it's convenient to use it to kill poles of something at infinity. If you multiply, say, by delta, that makes the weight higher. And that's how we search for these things. And then it's almost exactly the same for 24 dimensions, you just change the numbers a little bit. So okay, so that is written down the functions. Now this completely solves the linear program.
Right, but
So
didn't
phi
show us
is,
positive.
I didn't show it's positive. That's right. But it writes down the function. Yeah.
so, for E8, phi and C is a cusp one. For, the even ones, the ones that actually work with, so phi is a cusp one for E8.
When they have negative power, remember these things have negative powers in the expansion
Negative powers.
because I'm dividing by delta.
Dividing the delta, but
Yeah.
delta vanishes at the cusp
So yeah, but this has
vanishes to all the two.
so it's true. This does vanish in that cusp, but it's not automorphic.
Why
It's-
is it automorphic?
Hmm?
Why is it not?
Because E2 is not automorphic.
Oh, there's E2 in
Yeah.
Sorry, okay.
Yeah, I can show you the form. I have,
Yeah.
yeah. Okay. All right. So anyway, I'm a little short on time. I just want to mention one thing, just from, number theory bias, but you still have to show positivity. But I mean, already half the positivity essentially comes from the way these formulas are written. You have to show if you subtract one side from the other, you get another positivity, and it's using the theory of Q expansions. I think you could probably just give a proof by hand, but then it's very easy to give a rigorous proof on the computer, even with integer arithmetic. You can convert it to a question about polynomials, and so she used interval arithmetic in her paper, and then we used Sturm's lemma on polynomials, which guarantees a polynomial doesn't vanish on an interval. So the positivity is pretty straightforward to show. There's nothing really.
Ask the computer to draw the graph. It's obvious.
It's obvious from the graph. It's obvious at the two extremes from the theory, the Q expansions, and you could bound the. So actually, she used Klusterman's sums, which I thought you would appreciate in her paper. Okay. Okay. I just have 2 minutes, but so I think at the risk of completely losing anyone who's not in automorphic form, since it's only 2 minutes, I'll take that risk. One thing that's very striking about this breakthrough Maryna made is that it uses these modular forms of negative weight, which have poles at infinity. And these are things that don't fit at all well into the representation theoretic framework, say, of automorphic representation. So the modern definition of automorphic form has a growth condition in it, has an assumption of polynomial growth. So none of these things I've written down will qualify because we're dividing by delta, and delta, 1 over delta grows exponentially. The J function, which of course has deep arithmetic significance, is something that does not count in the realm of automorphic representations. So one question that's been kicked around is, do eigenfunctions, so basically to be an automorphic form, you have to be invariant under a group and satisfy some differential equations. So do eigenfunctions on higher rank groups automatically have polynomial growth? So we have examples like the J function for SL2 that have exponential growth, but no one has ever seen an example, say, on SL3. There's something called the Kircher principle on the symplectic group that rules them out in holomorphic settings. Have polynomial growth or not. So I think it's interesting because the examples are clearly very useful here for SL2. And there's a conjecture of Miatello and Wallach that asserts they don't. So I want to mention a theorem my student Dan Trin, who just defended his PhD last week, and I have proven. So let me try and get the right the statement's a little technical. Okay, so we're basically ruling out the analog of the J function for SL3. And there's something called a spectral parameter, which is indexing the differential equations. So I need to know the spectral parameter is in general position. Otherwise, the argument becomes more complicated. It's probably still works. Polynomial growth must occur, or else the Fourier expansion of the form, which is something like its Q expansion, does not converge. By that I mean does not converge absolutely. So since in the theory of automorphic forms, no one has ever seen an automorphic function whose Fourier expansion didn't converge, this gives pretty strong evidence for the conjecture there. And if you limit it to saying that's exponentially growing with a particular bound, you can show that all the Fourier coefficients have to in fact decay. None of them can grow at all, which is not what happens for the J function. So let me just put the student's name here. So there is, I guess, a little bit of hope that at least in higher rank groups, there won't be an issue with the representation theory not covering the objects because there aren't going to be any objects to worry about. At the same time, that's sad because